Hello, my name is Harrison Fisk. I manage the data performance team at Facebook, and today I'm going to be talking to you about MySQL for messages. This is a new deployment of MySQL at Facebook, and so I'll talk a little bit about kind of the background, about why we chose MySQL, what features were important for MySQL, and finally the advantages that we kind of get from this architecture. So a little bit about the background of our messages system. So our traditional messages system, which was built around 2010, is designed around a seamless messaging type architecture. The idea here is you could have email, SMS, web chat, all of these things all working together kind of in a single type messaging system. Now, the backend for this actually worked very similar to email. So essentially, you'd have things delivered into a single source of truth mailbox model, and then you'd have the clients could log in and say, hey, are there any new messages for me? And then it would download and sync those up. This was designed for web browser primarily. So back in 2010, the majority of Facebook users were coming through web. And this worked really, really well for the web browser interface. So basically, someone opens a web browser that keeps a connection and can download new messages essentially as they're coming in. The other big thing is we wanted to enable people to be able to have a more email-like experience where they could basically view all their messages historically as well. So we basically had to create this gigantic archive, essentially, of all these messages so you could scroll back and see these old messages. And that meant we had to build this based on hard drive technology because we needed this large, huge retention, essentially, of data. So now this message system worked really well for a long time. However, something started changing in Facebook. And that is mobile-to-mobile messaging. So mobile-to-mobile messaging started to become a very large, important use case for Facebook. So this has a lot of different paradigms. The first thing is the actual paradigm of the actual chat itself works a lot different. So in an email-type system, you have one large email sent. It's asynchronous. You get it kind of a little bit later. Whereas mobile-to-mobile messaging, there instead ends up being a lot of back-and-forth communication going on in real time. So it's a much more of a synchronous type model than the asynchronous model there. The second thing with mobile-to-mobile is mobile phones themselves have a much different network architecture. So the first thing is mobile phones can come and go a lot more frequently from the network. Whereas web browsers, typically keep them open, you're always connected, things are synchronizing well. Mobile-to-mobile phones will come and go all the time. The second thing is mobile-to-mobile. Mobile phones have much less network bandwidth. So we can't be polling constantly, checking for new messages. Instead, we need to switch from a pull model to a push type model. So we looked at this and decided, OK, we could build something better. And so what we've done is we built a brand new system that we're calling Iris. This is actually now deployed fully into production. It's handling all of our mobile-to-mobile messages. Many, many millions of messages per second are currently flowing through the system. So when we're building Iris, what were some of the goals that we were looking at? First is it was designed primarily to support this mobile-to-mobile messaging architecture. What does that mean? Well, we came up with basically 3 criteria. First, we wanted to improve response time. So when someone sends a message, until they receive the message, we wanted to get that as fast as possible there. Typically speaking, single-digit milliseconds or less for the actual storage backend itself. Next, we wanted to improve reliability. So when you look at mobile-to-mobile, we're comparing to things such as SMS and other sorts of telecom-type levels. So we wanted to get as reliable, at least, as an SMS-type system. And finally, we wanted to improve consistency. So nowadays, people tend to have multiple devices. So they have a phone, they have an iPad, they have the web browser, and so on. We wanted to make sure they were all seeing the same exact data and improve our consistency between all of these devices. So we built Iris to do this. So what is Iris? Iris is essentially a big queue. So we have this queue set up, and all messages come in, flow into this queue. And then you have things that can download and read data from this queue. What are types of things? Well, first, messengers. This could be phones, this could be iPads, and so on. But we also use our traditional messaging system essentially as a new subscriber to this queue. So we're able to leverage our existing system essentially as an archival type storage in order to do this. So we took our existing system, added this new queue on top of it. So to look at it in a little more detail, this is how Iris kind of works. So on the left here, you can see you have myself. On the right, you have my wife. I should actually probably say my lovely wife. She might be watching on live stream. And so essentially we have here, we have her message queue. So this is how her queue is looking currently. Notice we have a couple of different pointers here. We have an app. This could be her iPhone or whatever. Notice there's a couple events behind. Maybe it's been off. She's been watching a movie. Something's been going on there. And then we also have our disk queue as well. So this is a pointer to our traditional messaging system in order to download. So now let's say I send her a new message. So this new message goes to this Iris service and basically creates this new sequence, this new message essentially being added into that queue there. At the same time this occurs, we'll kick the archive and basically say asynchronously download this message. So that will then advance, download, and send this new message into the traditional messaging system for permanent storage on disk. And now at some point in the future, her device will come back online. So maybe the movie gets over, it turns it back on. And then what happens is it sends a get diffs, which will basically allow it to download and get just all the exact changes needed in order to resolve back to that. OK, so it's a relatively straightforward type system of this queuing with multiple readers going on here. So now what this enables as well is this enables a tiered storage type setup. So at the bottom, we have our long-term storage. This is stored on disk. This, again, uses our existing messaging infrastructure. And then on top of that, we were able to build these new levels, essentially of memory and flash. So the memory level generally actually has a retention in minutes. So we're able to keep the most recent message to message essentially in memory and Iris cached in order to make that even faster. But now we need to persist it to somewhere, and that is where we persist it down to flash. We typically have weeks retention worth of messages in flash, so that way if someone comes back online after being on vacation or something, you can get those very quickly from flash. And then we have the traditional system storing the hard drive here. So I've talked a little bit about the top part, which is the memory, which is Iris, and the bottom, which is hard disk, which is the traditional storage. So now what can we use for the middle part here? So we want to use something to essentially store and persist this data to actually flash. So what we did is we looked at what our needs for this were. So the first, this is going to be directly user-facing. So users are going to actually be sending messages, and they're going to be writing to the system, and then having to read data from this as well. So because of this, we wanted to, first of all, very high reliability. So many, many nines. You hear 5 nines, whatever. But we wanted to get as many as we possibly could. The second thing is we wanted a very low variation in response time. So when someone sends a message, we want to make sure it's going very, very quickly. Again, single-digit milliseconds or less was our goal. This is for both reads and writes, so both the senders and the consumers. And the final thing, we had a short retention. Because we're going to be draining to disk, we don't necessarily need to store the data permanently within the system. So we took a look at many different options out there. So there's a lot of different storage engines, different backends that are available, open source, commercial, and so on. So what are some of the different options we looked at? So we had things like MySQL, HBase, Rocks, Redis, Mongo. We looked at some special queuing systems, all of these sorts of things. And at the end, we decided to go with, as the name of the talk suggests, MySQL. So now why did we go with MySQL? So first, Flash optimization. So we've been running Flash on some of our other database tiers for a very long time. So we have experience with managing MySQL's access and reads and writes to Flash, things such as write lifetime and optimizing its access, all those sorts of things we've spent a lot of time already doing. The second thing is the overwriting of data actually happens quite a bit. Because of the fact that we have all these queues that are constantly being appended to, we actually write to the same page of data in the B tree repeatedly. So even though it seems bad for the B tree for writes, we're actually able to slowly sync these B tree pages to disk and actually optimize the flash writes as a result of this. The third thing is it's very good at minimizing latency variations. So again, we spent a lot of time optimizing MySQL, reducing the amount of stalls that we see, so we're able to leverage this already existing experience. And finally, the last thing, it's a proven technology at Facebook. We're already running many large-scale systems on this, so we're able to basically take the same exact operations team, all the software automation around it, and leverage that as well. However, we had some really big concerns when we were looking at using MySQL for this. So why would we not want to use MySQL? Well, there's two big things there. First, write scalability. So this is a very, very write-intensive application. For every message sent, we're going to be writing into this queue. for every message received, we'll probably be doing reads as well. But we actually will get those reads, a lot of those through cache, so writes will actually become the dominant workload of the system. In MySQL, replication has been a very big bottleneck for a number of writes. Single-threaded replication can't keep up with that. And the second thing is reliability. So again, reliability is a very key tenet for us. So there's two parts of this. First is data loss. MySQL replication is asynchronous. So if servers crash, masters crash, we could potentially lose data. That's no good. And the second thing is the actual failover time, the actual time it takes between a master fails until we can promote a new one in order to start receiving the new writes. So we were looking at this, and we happened to, at the same time, be upgrading to MySQL 5.6. So we're looking at some of the new features in MySQL 5.6, and it turns out there's actually a lot of good new things which actually help solve those problems. So to us, it was a super release. All right, so let's look at what those new features are, how we actually use those, leverage those to actually produce this system. So the first is write scalability. OK, so traditional MySQL replication, very, very briefly, for the 3 people that don't know how MySQL replication works, is essentially you have a master and a slave here. You then do the write to the master. It writes to the bin log. There's then an SQL thread, or the IO thread, which downloads them, writes it to the relay log. And the SQL thread then applies this. Typically speaking, you can do a couple thousand writes a second. This replication keeps up no problem. We're using this very widespread already at Facebook. Lots of experience dealing with MySQL replication. So 5.6 has a couple of new things to add to the replication. The first is something called GTIDs. So Jay mentioned this a little bit in his keynote, but kind of in a little more detail. What this is essentially every transaction in replication gets tagged with this unique ID. Pretty straightforward. So why is this important? Well, it's important for 2 things. One, when you're doing fast failover, it actually makes reparenting much easier, faster, and efficient. And the second big thing for us is crash recovery from multithreaded slave actually works with this. So multithreaded slave is an important thing for getting our write throughput up. So this is how multithreaded slave now works. So essentially, you still have the IO thread downloading the relay log here. So you have one thread still downloading. Typically speaking, downloading the binary log is not a bottleneck. Download's very, very fast, efficient, hundreds of megs a second, not a big deal there. Where it becomes slow is the actual application here. So instead, what we have is we have the SQL thread, which now reads, and rather than executing directly, it queues them out into different events. So this coordinator thread basically just dispatches those. And then you can have a configurable amount of worker threads that actually apply the changes. So there's a couple of big limitations on this that we had to keep in mind. The first is that in MySQL 5.6, these things are only parallelizable based on the schema or the database that they're in. So when we created this, we had to make sure we actually had lots of databases and schemas all on the same instance. So we actually ended up creating hundreds of instances, hundreds of databases on the single one. And then we could crank up the parallelization as needed to make sure that these can apply things. We did a lot of testing on this, lots of bug fixes and so on. In our final tests, we were basically able to go from single digits of thousands of transactions per second, 5, 6, 7,000 transactions per second, to a multitude of 10 to 20 times that. So we're easily able to get up to 50, 60, 70,000 transactions per second on a single instance of MySQL. So basically removed that write bottleneck from the equation in order to enable MySQL for this. The second thing is reliability. So how do we get the better reliability for MySQL? Multitude of nines. So what we first did is we used something called semi-synchronous replication. Who here has heard of semi-synchronous replication? Only a couple of you. One of the best kept secrets of MySQL, in my opinion. So this was added in MySQL 5.5. MySQL 5.6 has lots of enhancements. We've done some enhancements to it as well. But basically, in semi-synchronous replication, what happens is your application still writes to the master, same exact thing, still replicates to the slave, same exact behavior. Now what changes is the slave will now actually acknowledge back to the master. So whereas before the slave just kind of writes, or the application writes, and then presumes the slave will finally get that change at some point, instead now the slave is acknowledging back to the master that it received this event. And then finally the master can actually acknowledge back to the application that it's received it. What this basically says is when you do a commit statement, you can guarantee that at least one slave has also received that data change. So now we're no longer relying on single node reliability. Instead, we can make sure that we have multiple places that have that data. What's the drawback of this? Well, of course, the big drawback is now you're waiting for this extra network round trip within there. Practically speaking, we are seeing well under 1 millisecond increased latency time here. We're doing these acts within the same data center region, very, very quick and efficient. So what does the semi-sync part mean? Well, the semi-sync part basically means it's only waiting for the slave to acknowledge it has received that change. It may not actually be applied, so if a slave is lagging, the I/O thread may be downloading much faster than the SQL threads can apply. That's fine. We're still going to be able to acknowledge things because we're downloading those events. So that's the semi part. I have no idea why they came up with that name, but that's how it works. So how does the master actually do this commit path? So we can think of it this way. So we basically have our prepare phase up top. We then write to the bin log. So we have written data to the bin log, and we make it available to the slaves as well. So now in parallel, we can do a binary log sync. So this is where we're calling something like fsync to actually commit the data to disk. And then the slaves are going to be receiving this data in parallel. Again, these are all happening in different threads here. So then the slaves will acknowledge. So we're only waiting for one of these slaves to acknowledge. Slaves can only acknowledge when they're totally caught up. So it's possible that one may be lagging behind or whatever, so only one may be acknowledging. That's fine. We just have at least one guarantees. And then finally, we can actually do the commit and return the commit back to the client. So now we know our data is persisted. This message that you've sent has definitely been written. We can now return back to the client saying, OK, your message is guaranteed that it will be delivered. So now how do we actually use this? So what we've set up is we basically have a system such as this. So we have a master and a slave, 2 copies of data essentially. And then in order to have additional redundancy for the semi-sync, we actually ended up deploying something called log tailors. So these log tailors are systems that don't have any actual data themselves. They are only to actually acknowledge and download the binary logs. So they basically act as slaves and stream binary logs as fast as they can, but they don't have the actual data. Why did we do this? Well, it allows us to basically put lots of log tailors on a single physical machine, so we can basically reduce the footprint, the amount of hardware required in order to deploy this type system. The other thing to note here is notice that we have log tailors on both the masters and the slaves. Why did we do that? Well, because we want to be able to fail over to the slave very, very quickly, and it's not a lot of additional hardware because of the fact that we can oversubscribe these log systems. Okay, so we have them pre-set up, ready to go here. So now that we have this, how does fast failover actually work? So this is our kind of production system, right? We have our master, we have the log tailors, we have an application writing, in this case Iris, writing data to the master, being downloaded by the slave. So the first thing, so we have our timeline going on here. So the first thing is the master fails. Oh noes, the server's failed. Bad things have happened. So now what happens is we first have to detect this failure occurs. So the way we do this is the log tailors and slaves all basically vote as to whether the master is available or not. So they all talk amongst each other, and they do some voting in order to decide if the master is alive. This can take up to 18 seconds. We basically do a 6-second heartbeat and requires 3 of the failures. This is somewhat tunable. We're still playing with exact numbers, but we're right around 18 seconds in order to determine that the master has failed. So now that the master has failed, we disable it and say, OK, no one can try to ever write to this master. We then need to apply missing events. So because I said only one of them are guaranteed to be the most recent one for the semi-sync, we will take whatever one is the most advanced. So we have our 3 tailors. We have to go and basically ask them, OK, what position, what coordinates are you at? You're at the farthest most coordinates. So we'll take all the events that are missing from that and apply it to the slave. Typically speaking, this is only a couple events, because again, they're all kind of in the same region, all downloading, but it could be a little bit more data depending on how that goes. So now we've applied these missing events, took a couple seconds, and now we need to reparent to the new master. So this is basically just switching everything over, changing log tailors to go off there. This, again, is where GTIDs and so on make this much more simple and straightforward. And then we need to enable the new master. So now we enable the new master, writes can resume, and everything is happy. So the results of this new fast failover system, 2 things. First, no data loss. So because of the semi-sync, we can guarantee that there's definitely no data loss on our systems. And the second thing is under 30 seconds for master failures. Completely automated, everything kicks off because of the way we've set this up with the no data loss. So the summary of this, what are the takeaways? So this is kind of the big picture. So we have this new system we've set up. So we took our existing messages system, and we put this new system in front of it, Iris, using this in-memory queue, which persists down to MySQL on Flash. And this enables us to have a lot of different properties. The first, it gives us the tiered storage, so where we can keep more recent data automatically in memory and Flash. Gives us the benefits of those systems without having the other one. The next thing is there's a lot of different systems available to you. We chose to use MySQL for this particular one. We had to look at a lot of different solutions and came up with that. And finally, the last thing, MySQL 5.6 has really enabled us to switch the sweet spot for MySQL from being these heavy read OLTP applications to something like this, where MySQL doesn't even really the permanent store. It's a little bit more of a week-long type caching system. So that is it. Thank you very much. Any questions? All right. Question in the back? You want to come up to the mic so I can hear, maybe? Run quickly. Sprint. People waiting.
I can't do that. So do you try and handle split brain scenarios between the master and the slave? What if both of them think they're master?
Yep, so the question is, do we try to handle split brain between master and slave? So we have a couple of different things here. The first is we actually have some stoneth type stuff, so we actually will try to shut down the master if we can, in order, before we do the fast failover, to make sure it's really dead there. The second thing is we're actually deploying a new system right now where we actually have the master participate in the votes as well. And if it notices that everyone is voting it down, we will actually make sure, or if people aren't voting it up, it'll actually shut down as well.
But that still assumes the network never partitions cleanly across, right?
So we have an odd number of voters, so it's based on a quorum.
Thank you.
In order to vote down or up. Yes?
And what actually is the system that manages failover and switch from failed master to another slave? Is it something open source?
So how we actually do the failure?
Yeah.
So we actually, it is not open source. So we have our own tier configuration system, which denotes what's a master, what's a slave and stuff. It's built on Zookeeper. And so basically that just is a Zookeeper-based system for configuration, so that way everyone knows what to talk to. And the actual failure logic itself is pretty straightforward. It's not much different than some of the stuff that already has been created open source by the MySQL Replication team. There's actually an open source Python things which can do master failures and repurposing and so on.
Okay.
Yep.
Sorry. Hi. The logs or the pseudo slaves that you have, are those physical machines, or those are just VMs, or they're just sharing the same server? How do you
The log tailors, you mean?
Yeah.
So the log tailors themselves, we don't use a lot of VMs, but basically it's just something running lots of instances. In this case, we actually use MySQL binlog. There's an actual option in MySQL binlog to download binary logs. So we use that combined with a little monitoring daemon in order to do that. And we just basically put like 40 of them or something, or 50 of them on a single physical machine to download.
So how do you do, if that machine goes down, what do you do?
So if that machine goes down, well, we lose the log tailors. And so basically we have a system that then starts 50 new ones on different systems. So that's a separate monitoring. It doesn't actually impact production to have one of those go down. All right. If not, thank you very much.